Hey, good evening or morning or afternoon or midnight or wherever you might be. Welcome back. This is going to be lesson 8 of unit 1 for calculus. Today we're going to talk about the idea of continuity. Now last time we talked about the idea of discontinuity. We did define what continuity was at a point, and if you remember, a function is only continuous at a point if the limit as x approaches that point is equal to the function's value at that point. Okay? Then we went into all the different types of discontinuity, the removable, the jump, the infinite discontinuities, and how to determine those analytically. Today we're going to take that idea and we're going to figure out a way to make a function continuous given a little bit more information. Okay? So with that said, the objective, I can determine if a function is continuous over a given interval. We kind of talked about that a little bit last time. We're going to add to that. And then we're going to do some practice problems here and then get into a different idea. Remember, a function is continuous at a point when the limit as x approaches that point of the function is equal to f of that point, or f of that x value. So again, understanding the left-hand limit, what's it getting close to, equals the right-hand limit, what it's getting close to. Since those two things equal the same limit, same value, then the limit exists, and it's whatever that height is. So we know the limit exists. Now we have to see if the point is the same as the limit. If the limit is different than the point, let's say the point is up here, but the limit's down here, then the function is not going to be continuous at that point. So we want that point to basically fill in that gap, if you would. Okay, so that's the definition, just rewinding and remembering what we did last time. And so here's an example of that. We have f of x being a piecewise function. F of x is equal to x squared plus 7x plus 12 over x plus 3, and that's for x not equal to negative 3, and 4 for x equal to negative 3. Okay? And the question is f continuous at x equals negative 3? So there's 3 things we have to check for continuity. We need to check the left-hand limit, the right-hand limit, and the function's value. So the limit as x approaches negative 3 from the left of f of x, the limit as x approaches negative 3 from the right of f of x, and f of negative 3. Those are the 3 things we need to check. We check these 2 first to see if they match. If they match, then the limit exists, and then we check to see if that limit matches the function's value. If they match, then it's continuous. So in order to figure out the limit from the left, which piece are we going to use? We're going to use the upper piece because this piece is only at negative 3. We are looking for all the values that are left of negative 3. So remember, we're going to check for substitution. So I plug in negative 3. Negative 3 squared is 9 plus 7 times negative 3. Well, 7 times negative 3 is negative 21. So 9 minus 21 plus 12 is 0. And then negative 3 plus 3 is 0. So we get an indeterminate form when we do substitution. We're going to get the same thing on this guy because we're going to be using the same function. So the way we go about that is to figure out the factors if we can. So this is going to be x plus 3 times x plus 4 all over x plus 3. And that is the limit as x approaches negative 3 from the left. We can see that the x plus 3's reduce. And so we're left with the limit as x approaches negative 3 from the left of x plus 4. And so we can plug in negative 3 plus 4, which is 1. And so we have our left-hand limit. We're going to do the same kind of work, same type of thing on the right-hand limit. And in fact, it's going to be the same exact thing because we're using the same part of the function. If this said x is less than negative 3, and this piece said x is greater than negative 3, then we'd be using this function for the right-hand limit. But because the left and right-hand limit are both comprised using the same part of the function, it's going to be the same work. So I'll just go ahead and write down x plus 4, and again we get 1. So we can say the the limit as x approaches negative 3 of f of x is 1, and that is because the left-hand limit matches the right-hand limit. For the other one, for f of negative 3, well, f of negative 3 is equal to 4, because that's just the value at that point. What can we conclude? We would say since the limit as x approaches 3 of f of x does not equal f of negative 3, then we would say f is not continuous when x equals negative 3. Okay, so we did that. It's not continuous. Now the question is, what kind of discontinuity do we have? Last time we talked about the idea that if we can factor and reduce, that is a removable discontinuity because we're removing the problem from our function. So we can say, we could say this is a removable discontinuity. Now, in the past, you guys are probably used to calling it a hole. That's a layman's way of saying it. It's a removable discontinuity. If I was to graph this function, I know that this function is exactly the same in every way as x plus 4, because this is exactly the same as this. So we have a linear function. So we're going to shift up 4. We have a linear function, and we have a slope of 1. So it looks something like this, except at negative 3. At negative 3, we have a hole. The limit, you can see, the limit is 1. The limit's 1. From the left is 1, from the right is 1. But the function's value is 4, so we put a point there. So that is the graph of our function. Okay? And so just to recap, we're going to check our limits, our left-hand limit and right-hand limit. Now in the work, I didn't expressly do that, but you should do it according to this method here. Okay? And you'll see hopefully another example in the near future where this is actually more beneficial. And so we can see that the limit is 1, and we know it's a removable discontinuity because those canceled out, or they reduced. And we'd say the limit does not equal the function's value of 4. Therefore, we would say that it is not continuous at negative 3. Now, again, there's the graph. That looks good. Then the last question is, how could the function be fixed or expanded in order to make the function continuous? Well, how would I make this continuous? What I would have to do is move this point down to here. So if I can move that point there, it's continuous. So I could do this by saying, hey, let's just change this to 1. Then it's a continuous function. But we can really simplify this to just say the continuous function that's equivalent to this everywhere except that point, and therefore would make it continuous at that point, is if we just use the linear function of x plus 4. So this is the expanded form, in a sense, that makes the function continuous. This is this, but it fixes the whole, essentially. Okay? So that's one example of something that we did yesterday. Let's take a look at something a little bit different. It's new in terms of the type of example, but it's not new in terms of the concept. We're talking about continuous here, continuity. Now the question here is, what is the value of k that makes the following piecewise function continuous? What is the value of k that makes the following function continuous at x equals negative 1? So I should probably go ahead and write this down. We've got 2x squared minus 5 for x is less than or equal to negative 1. And we have 3x plus k for x is greater than negative 1. And that is our function h of x. So we want to make this guy continuous by figuring out what k value we'll plug in there. Now graphically, you guys can kind of visualize this graphically. Hopefully you have a pretty good understanding of this. Here we have a parabola. 2x squared minus 5. So we have a parabola, opens up, it's shifted down 5 units. So it's whatever this parabola is. And then here we have a line with a slope of 3. Now this k is the y-intercept. So essentially this k is going to take this line and it's going to move it up or down. Okay? So we have a parabola, whatever that parabola looks like. And graphically, we can do this kind of quickly, but analytically is the more important case here. 2x squared minus 5 is just a shift downwards of 5, and then we have a steeper slope pattern because the a value is 2, but that's not important. For all values less than or equal to -1. So really, all we care about is this part of the graph, right? That's all we care about for 2x squared minus 5. Then the 3x plus k, I don't know what k is. Let's just say that this is k here. Well, then the graph would look like this. That's not continuous. Oh, sorry, not there, at -1. So at -1. It's not continuous. So what would we have to do in this case? We'd have to take that line and shift it down until that point lines up with that point, okay? So the idea is, whatever that is, this has a slope of 3. So if I want the point to start there and it has a slope of 3, we're going to go up 1, 2, 3 over 1, and then we have our line. And so if we can draw the parabola and we can draw that line with a slope of 3 so that they intersect there, that would make the function continuous. And then you can see the k value is actually -1. But the graphical approach, again, is not the most proof-oriented approach. And when we get to more complicated things where k is not just a vertical shift up or down, it could be a horizontal shift, it could be a stretch or anything else, it gets really weird to try and think of it graphically. So we're going to think about this analytically, and this is the approach that you really should be going about. Remember, we need to figure out the three things. We need to figure out our left-hand limit, so the limit as x approaches -1, right, of h of x, from the left. We need to figure out our right-hand limit, limit as x approaches -1 from the right of h of x. And we need to figure out h of -1. All three of these things must be equal to each other. If these are all equal to each other, then it's a continuous function at -1, at x equals -1. So how do I figure out the left-hand limit at -1? Well, I'm going to use the upper function because this is for all values that are less than -1. So I'm just going to plug in -1 to that. So it's going to say 2 times -1 squared minus 5. Okay? And then we can simplify that. -1 squared is 1 times 2 is 2 minus 5. That's -3. So we have our left-hand limit. Our right-hand limit, notice this is inequalities here. It's not just equal and not equal. For the right-hand limit at -1, we're going to use the bottom function. Oh no, there's two variables there. It's not that big of a deal because you know when we're taking limits, we know what the x value is. We're trying to approach x equals -1, so we're going to plug that in. 3 times -1 plus k. And so we simplify this, we get -3 plus k there. Something seems off. Oh, not -3, 3. There we go. That would have been, no, that is -3. What's going on here? What's going on here? -1, 2 is -3. Okay. Okay. So, okay, that makes sense. All right. And then the last part is we got to figure out what h of -1 is. Well, h of -1 is going to be using the top equation because that's what it's equal to. So that would be 2 times -1 squared minus 5. And then simplifying that, we already did that on the other side. So all three of these have to be equal. If these limits are equal and equal to the function's value, then all three of these statements need to be equal. Now, since these are the same, I can kind of just ignore one of them and just focus on the other. So -3 equals -3 plus k. And then solving for k, we would end up with k equals 0. Okay? And so that tells us what the k value needs to be. If I shift down 5, okay, and then I have my slope pattern of up 2 over 1, and then it would be up 6 over 1, 2, 3, 4, 5, 6 over 1. And so we get this parabola that looks something like this, but I only care about this point, and that's included there because it only goes to -1. And then we want this to be continuous following the slope of 3, so up 1, 2, 3 over 1. There's our graph. What is the k value? The k value is 0. The y-intercept is 0 there. I was getting a little confused on why this wasn't working because the previous graph I gave, I wasn't following any specific slope pattern, so I wasn't necessarily determining the value of k correctly. Now, with that said, we know that if k is 0, this will be a continuous function at x equals -1, or the function will be continuous when x equals -1. Okay, so we have our left-hand limit. We have our right-hand limit, and we set them equal. We have our function's value, we set it equal, and then we solve for k. Now, the way I did it on the lesson here is probably not the best way. This is the more direct approach. It's going to make sure that you get it right every single time. It's the left-hand limit equals the right-hand limit equals the function's value. I'll tell you right now, a lot of students struggle with this idea, with this concept. It's not a difficult concept. In all reality, it just means you need to practice more, essentially. Okay? There's a lot more difficult things than this. You're just setting things equal. If you're struggling with this, make sure you're reaching out to me. All right, with that said, let's go ahead and have a practice problem with this idea. So you guys go ahead and pause the video and see if you can come up with the correct answer here. And then when you're ready, push play and see how you did. So for your practice problem, you got f of x equals kx squared plus 7. And that's for x is less than 2. And you have 2x plus 1 for x is greater than or equal to 2. And we're trying to figure out the k value that makes this function continuous when x equals 2. So you can see k is no longer just a vertical shift. So it's a little bit more difficult to wrap our heads around. What k is a vertical stretch. So it's taking this parabola and is doing this, right? And so trying to understand what that does to make it continuous is difficult graphically. So what we do is we check our limits. We say, what's the limit as x approaches 2 from the left of f of x? What is the limit as x approaches 2 from the right of f of x? And what is f of 2? If this is going to be continuous, this whole statement must be a true, valid statement. And so we determine each of these and set them equal to each other. To figure out the left-hand limit of 2, we're going to use the upper function. So that's going to be k times 2 squared plus 7, right? We're plugging 2 in to x, and k is just staying there. For the right-hand limit, we're going to use the bottom function. So that's going to be 2 times 2 plus 1. And then for f of 2, we're going to use the bottom function again because that's equal. So that's going to be 2 times 2 plus 1. Again, those are the same, so we don't need to worry about setting those equal per se. But we still want to have three things equal to each other. Simplifying this, you end up with 4k plus 7 equals 5, and then equals 5 again. Don't need that one. So 4k plus 7 equals 5. We'll subtract 7, so we end up with 4k equals -2. And then we'll divide by 4, so k equals -1/2. All right. So that is the value of k. Now, if you want to think about it graphically, the first one is a parabola with a vertex of just up 7. And then we have the bottom thing, we have a line, so it's up 1, and then a slope of 2. 2 and 2. 1, 2, 3. And we're looking for a parabola. This is for every value greater than 2, greater than or equal to 2. So there's my line. And so we've got to figure out the parabola so that this is the vertex and it hits that point. Well, we automatically know it's got to open down. That's why the k value is negative. But to get to this value is a little bit more difficult graphically. That's why we look at it analytically. All right. Again, checking the left-hand limit, the right-hand limit, and function's value. Determining all those, setting them equal to each other. And then solving for k is the way to go. Again, the better way of doing it is what's on the board, not what's on the lesson. All right, let's shift gears a little bit here. And this is just a statement of fact. If a function is a composition of two other functions, then we can say it's a continuous function if the pieces of the composition are continuous. Okay? So if f is continuous at a specific point, and g is continuous at a specific point, or sorry, continuous at the result of that specific point on f, then g of f of x is continuous at c. That sounds crazy. That sounds like what the heck is he saying here? But let's take a look at an example. Why is the graph of 3 times x minus 1 squared continuous? Now let me write that down. Y equals 3 times x minus 1 squared. Why is that continuous? Now, most of you are going, well, it's a parabola, it's continuous, obviously. But I want you to look at it through a different lens. I want you to look at it through the lens of a composition of functions. So here's what we're going to do. We're going to say, what is the inside function? The inside is x minus 1. So let's say let f of x equal x minus 1. Okay? Then g of x would equal 3x squared, if you would. Okay? If the inside is x minus 1 and the outside is 3 something squared, right? 3 something squared, we can say that this function is a composition of these two. And let me show you. It would be g of f of x. If we took our f function and plugged it into this x value for g, we would get 3 times x minus 1 squared. So then we would say, therefore, g of f of x is equal to 3 times x minus 1 squared. So that's step 1. Identify your pieces of your composition. Okay? Now, we would then say, is this continuous? Well, are all the pieces of the composition continuous? We would say f of x is continuous, right, for all real numbers, since it is linear. Okay? So we know that the inside function is continuous for any number. Now, we can say that g of x is continuous. Well, how do we know that? We know g of x is continuous, I should say for all real numbers. How do we know that? Since it is quadratic. Okay? So since f of x is continuous for all real numbers, that means we're going to get answers out every time. And then g of x is continuous for all real numbers, so whatever numbers I get out for f of x, I plug into g of x, and we know that that's continuous as well. Therefore, g of f of x, which equals 3 times x minus 1 squared, is also continuous. Now, this is going to seem picky, but that is the thought process. And if you have a question like that anywhere, that's what should be written down to express what you are doing. Since this can be broken up into a composition where the inside is linear, and we know that that function is continuous, and the outside is quadratic, and we know that that is continuous, then the composition of those two functions will also be continuous. Pay close attention to the verbiage, pay close attention to the concept here, okay? And then we will, let's go ahead and take a look at and see how I wrote it here. I said let f of x equal 3x squared, so I actually did it a little bit differently, and g of x equal x minus 1, so I just flipped those. We know that 3x squared is continuous because it's a quadratic, since it's a parabola. Okay? We know that g of x is continuous because it's a linear function, so x minus 1 is continuous. Therefore, f of g of x is also continuous. The composition of continuous functions is continuous. And therefore, y equals 3 times x minus 1 squared must also be continuous. So that is my example. Let's go ahead and do a practice of these. So go ahead and read this, do it yourself, push play when you think you got it, and then you can compare it to my answers. All right, so here we have f of x equals the absolute value of radical x plus 3. Okay, and we're asking, is this a continuous function? Now, immediately you might recognize that this will not be continuous for all real numbers because the square root function has a domain restriction, okay? But yesterday we talked about the idea of continuous functions. A function is continuous if it's continuous for its entire domain. So really, we don't care about what's outside the domain, and what we really care about is what's inside the domain. So what are we going to do here? We're going to say let g of x equal radical x plus 3, and h of x equal the absolute value of x. So that's the composition here, okay? We know g of x is continuous over its domain, okay? And just to kind of discuss that a little bit, this is a radical function with a shift to the left of 3, and so it looks something like that. That's the radical x plus 3. You go, well, it's not continuous to the left of negative 3. Well, you're right, but again, it's continuous for all points of its domain. The domain of this guy is from negative 3 less than or equal to x less than infinity. So since it's continuous over its domain, it's considered a continuous function, okay? H of x is continuous for all real numbers. Okay, and that's true because it's an absolute value function, right? An absolute value just looks like that. It's continuous for all real numbers. And therefore, we can conclude that h of g of x, which is equal to, I missed that. I missed that statement. Absolute value of radical x plus 3 is also continuous. Okay, is also a continuous function. Okay, again, the verbiage is important. Okay, writing things out. And then we would say something along this line. It might be a good idea to insert this statement somewhere in here. We would say f of x is equal to h of g of x. Okay, and then we could even say this, therefore h of g of x, which equals f of x, is also continuous. Okay, so you can see in the previous one, well, it's just quadratic. We could just explain it that way. But the idea is to go a little bit, the concept was to look at it in terms of composition of functions. Okay, if each piece of the composition is continuous, then the function itself, then the composition is continuous as well. Okay, so not to belabor that point because we want to move on to other ideas here. Okay, so let's go ahead and shift gears here a little bit and talk about what's called the intermediate value theorem. Now, there's going to be a lot of theorems, but there's going to be 3 big ones in calculus that we need to remember. And really, a lot of calculus hinges on these 3 theorems. The first one is the intermediate value theorem, and it's really the only one we can really discuss at this point until we get to higher level stuff when we talk about derivatives and things like that. But the intermediate value theorem says this: if a function is continuous over a closed domain, okay, we'll say the domain is a to b, closed domain. If the function is continuous over that closed domain, then that function must obtain every y value between f of a and f of b. In other words, it's impossible for it to skip from this y value up to another y value without passing through all the y values in between. And at first you might go, well, I'm not fully understanding what that's saying, especially when I read all those words on the screen. But let's see if we can look at an example here. If I have a graph that goes from here, let's say, and it goes up and then it goes down. Let's say that's the graph. Now, I don't know what the graph looks like. Okay, I just gave you the graph. How nice of me. But let's say you didn't know what the graph looked like. Let's say that this was 2 and this was 7. The x value 2 and x value 7. Let's say that this was 3 and this is 9. Okay? Now the one thing I'm going to tell you, and in fact, let me go ahead and erase this and let's pretend we don't know it's there. The one thing I'm going to tell you is that this is the graph, well, 2 things. This is the graph of f, and I'm going to tell you that f is continuous for 2 to 7. Okay, so it's continuous, which means, over the closed interval, which means these 2 dots have to be connected somehow. There's no way around that. They have to be connected. Now, the question is, what does that imply? Well, the intermediate value theorem says that every y value between the value of the y value when x equals 2 and the y value when x equals 7 must be obtained. So we have a coordinate of 2, 3. and we have a coordinate of 7, 9. If it's continuous from here to here, that means every y value must be touched between 3 and 9. That doesn't mean that the graph is going to connect in a straight line. It could, but it doesn't have to. In fact, the function could do this. It could go blah, 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 right? Every y value was touched along the way. Okay? Now, you could say this. Well, I'm going to prove you wrong. Okay, go ahead and try. I could go up and then outside of the 9. That's fine. I didn't say you couldn't. But notice, if this function is continuous, then every y value from 3 to 9 is passed through somewhere in this interval. Okay? Every y value is obtained. It's touched. Well, what if you went down? What if you went down? Well, okay, go down. Every y value was touched. It was touched from here to here. Okay? Now, there's lots of different scenarios here that we could look at. We could say, well, what about this? Well, that's probably not the best example. I'll go up a little bit, and then down, and then up like that. Well, every y value was obtained between 3 and 9. The only example that there's only 2 examples that I can think of that contradicts that, and that actually contradicts the hypothesis. Okay? If I take this and I go like this, woo! Within 2 to 7, do we touch any values between 3 and 9? No, we don't. But this isn't a function, right? It fails a vertical line test. Okay? The other counterexample, if you would, and it's not a counterexample, is that if I'm going along here and then I jump and then I go along. You go, did it touch every y value? No, it didn't. From this y value to that y value, it did not touch. But what's wrong with this? F is not continuous. This is a jump discontinuity. And therefore, the hypothesis is broken, which means the intermediate value theorem doesn't apply. The function has to be continuous. And there is no example that I can give you where the function is continuous that you don't hit every value between 3 and 9. That's basically what the intermediate value theorem says. Let's go ahead and take a look at another graph. Maybe this will help you out a little bit. Here we have a graph of f from a to b. And essentially what I can do, since f is continuous over the closed interval, then we know that f will touch every value between f of a and f of b. I guess this is the graphical look at the statement that I gave you a second ago. Okay, so that's more of the formal way of explaining it, and this is just a specific example here. If I look at this example, it says that g is continuous over the closed domain of 5 to 9, closed interval. If g of 5 is negative 3, let me go ahead and write these things down. If g of 5 is negative 3 and g of 9 is negative 8, then what are values that g of x must pass through over the given interval? So we can graph this. We've got g of 5, 1, 2, 3, 4, 5, 1, 2, 3. And we've got g of 9, 6, 7, 8, 9, and then 4, 5, 6, 7, 8. So we have these 2 endpoints of our graph. We know that the function is continuous, so we have to connect those, and we have to draw it as a function. So what are some y values that are guaranteed to happen? Well, no matter what I do, I know that I've got to touch, let's see, every value between negative 3 and negative 8. Okay? So if I connect it with a line, if I connect it with squigglies, no matter how I connect it, every one of these values, every one of these y values will be crossed through, every single one of them. Now, you may draw the graph so that it goes up and then down. Does it pass through every y value between negative 3 and negative 8? Yes. The intermediate value theorem did not say anything about not passing through other points. It could pass through other heights, and that's okay. But it must pass through all of those other points, or all those points within that interval. So an example of this would be, well, it's got to pass through y equals negative 5, y equals negative 7.213, every value between negative 3 and negative 8. So all y's y values such that negative 8 is less than y is less than negative 5. Okay, I guess you could answer it that way. You can give specific examples, but I think that's a pretty straightforward idea. Every value between negative 3 and negative 8 must be obtained, or negative 8 to negative 3. So that's that. Let's go ahead and take a look at an example of what this looks like. And at first, when you read this, you go, this doesn't make any sense. How does this apply to the intermediate value theorem? But it's actually kind of cool when you see it, and it'll give you a little bit of a context to help you understand why the intermediate value theorem is important. The question is any real number exactly 1 less than its cube? Is any real number exactly 1 less than its cube? So what we're going to do is we're going to say, can we find a number such that it is 1 less than its cube? Okay, so we have this kind of equation here. Is any number x exactly 1 less than its cube, than the number's cube? So we have this equation here that's based on that statement. So the question is this equation a valid, true equation? Well, how could I know? How could I know? Is there any equation or any value so that it is exactly the same as 1 less than the cube of that? Well, the first thing I'm going to do is I'm going to subtract x from both sides. Okay, and we're trying to avoid any major kind of work here. We know that this function, just the x cubed minus x minus 1, is a continuous function. It's polynomial, right? And we know that it opens or goes upwards, essentially. The end behavior is that it goes off to infinity. So if this is true, if we can prove this, then that's true as well. Well, we know that this graph is x cubed. So that means it starts low down here, and then it goes high. And maybe it looks something like this. Okay? It's got to look something like that. It could do this. It could be really flat. It doesn't matter. But we know that it's got a little bit of a whoop in it, right? But we know that it starts low and it ends high, which means it must pass through 0. Okay? And if it passes through 0, that means we have a point. We have a point where this function is equal to 0. Now in this case, it's 3 times. In this case, it's only once. It doesn't matter. It does happen once. And since this equation is true, it follows that this equation will be true, and therefore we do have one. That doesn't really invoke the intermediate value theorem, but let's go ahead and take a look at the lesson, and you're going to see how that does invoke the intermediate value theorem. So again, first thing you're going to do is create an equation. So we have x equals x cubed minus 1. And then we're going to move everything over so it's equal to 0. Okay? So now maybe you didn't understand the graph very well. We know that this is a continuous function because it's polynomial. And we know that it's continuous from 1 to 2. Now why did I pick 1 and 2? Those are kind of arbitrary. But watch what happens based on the 1 and the 2. If I say let y equal x cubed minus x minus 1, and in fact, let me call it f of x equal that, then f of 1 is going to be 1 cubed minus 1 minus 1. And so that's going to be 1 minus 1 minus 1 is negative 1. So f of 1 is negative 1. And we know that f of 2, not f of 0, f of 2 is going to be 2 cubed minus 2 minus 1. So that's 2, 4, 8, minus 2 is 6, minus 1 is 5. So we got f of 2 is 5. The idea is this. Now I gave you a graphical approach a second ago, but the intermediate value theorem says this. Since f of 1 is negative 1, and f of 2 is positive 5, we know, since the function is continuous, that we have to connect these dots. No matter how we do it, no matter how we connect them, what happens? We know that it's going to pass through every point from y equals negative 1 to y equals 5. It's going to pass through every one of these points. Specifically, it's going to pass through y equals 0. It's going to pass through that green line there. And that's exactly what we wanted it to pass through. We know that there is at least one solution where this function will pass through y equals 0 because part of the function is below 0, part of the function is above 0. And as a result of that, it must hit 0 somewhere by the intermediate value theorem because 0 is between -1 and 5. And if it does, that means this equation is true, which implies that that equation is true. So therefore, there is a point that is exactly one less than its cube. Do we know what that point is at this point? No, we don't. We'd have to get our calculator out. We'd have to find the 0, but that wasn't the question. We just want to know if there is a point. Okay? So f of 1 is -1 and f of 2 is 5. And since 0 is between -1 and 5, we know that the function must pass through 0 by the intermediate value theorem, and therefore there is one answer. Now, somebody might say, well, why did you pick 1 and 2? Because I knew they worked. Well, what about me? I don't know what works. You're right. So you just kind of try and see what happens. So maybe you try the interval 3 to 7, right? Or closed interval. We look at those two values, f of 3 and f of 7, and we see what we get. Well, 3 cubed is 27, minus 3 is 24, minus 1 is 22. And then f of 7 is going to be way bigger because we're cubing here. So we know that this is going to be greater than 22. So that doesn't really help because we don't have a value, we don't have something that makes 0 between those. So what might be helpful is just to be a little bit more extreme. Maybe we pick a number that's like, the interval's like negative, -10 to 10 as an example. Well, f of -10 is -10 cubed is -1000, and then that'd be plus 10. So that'd be -990 minus 1 is -991, I believe. And then f of 10, well, that'd be 1,000 minus 10 is 990 minus 1 is 989. Is that right? I believe that's correct. So we can now say, since 0 is between -991 and 989, f of x must obtain 0, obtain y equals 0 for some x value such that -10 less than x is less than 10. Therefore, since that's true, since 0 is between there, it must hit 0, which means that function must be true also. So you kind of pick arbitrary ones, and you're looking for one that is less than 0 and one that's greater than 0, and therefore you would know 0 is between them. All right. Let's go ahead and take a look at this one. It says, let f be a function that is continuous on the closed interval 1 to 7 with f of 1 equals 0 and f of 7 equaling 10. Which of the following is guaranteed by the intermediate value theorem? So I want you to go ahead and pause this, read those answers, see what you come up with, and then come back and see how you did. All right, the key to this question is not, it did not say which of the following is true. It said which of the following is guaranteed by the intermediate value theorem. In other words, which one's true, but it has to be based on the intermediate value theorem. So we have the two coordinates here. We have f of 1 is 0, so I'm going to go ahead and graph that. F of 1 is 0, and f of 7 is 10. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have these 2 points. We know that this function is continuous over that closed interval, so we got to connect the dots. Which of the following must be true by the intermediate value theorem? Well, does f of 4 have to equal 5? Well, some of you probably said, yes, it does. Why did you put that? Well, because 5 is between 0 and 10. Yes, 5 is in between 0 and 10. The intermediate value theorem would say that the function must pass through y equals 5. But it doesn't say where it must pass through. And the assumption that you probably made is that, well, if it's linear, then yeah, it would pass through there. But nowhere did it say that this function was linear. And even if it did say it was linear, it would be true, but it wouldn't be true by the intermediate value theorem. The intermediate value theorem says take any continuous function and you will hit every y value between the two endpoints y values, essentially. So A may be true, but it's not guaranteed, number one, and it's definitely not guaranteed by the intermediate value theorem. B says f of x is 8. Well, f of x is 8 for some solution, or for one solution between 1 and 7. 1 and 7, here's 9 and 1. So it's saying that f of x equals 8 has at least one solution. Do we have to cross through that dotted line over this interval? Yes, we do. To connect from here to here, we do. So B is a true statement. C says f of x has to be negative 8. It has to be one solution. Do we have to pass through that point, or that y value? No, we don't, because we're looking at from 0 to 9 y values. Now, it could, but it doesn't have to. The intermediate value theorem says it has to. Okay, so C's out. And then f of x must equal 9 for at least one solution between 1 and 7. Now, 9 does get touched. Sorry, that's 10, not 9. Whoops. Let me raise this up a little bit. The 10, so 9. So does the value 9 have to be one of the solutions between 1 and 7? Well, 9 is between 1 and 9, or 1 and 10, therefore it must be a solution by the intermediate value theorem. So we have answers of B and D. If I were to put 10 instead of 9, then the answer would be no, it doesn't have to be over the open interval here. So right here, it's from open interval 1 to 7. So 10 does get obtained, but it doesn't mean that 10 is going to be another answer between 1 and 7. All right, last problem here. It's an exit problem. What is the expanded equation of g of x so that it is continuous over the interval 0 to 5? So go ahead and give this a shot, see what you come up with, and then come back and watch, see how you did. All right, we are looking to see how we could fill the hole, essentially. How do we expand this function so that it is continuous over the interval 0 to 5? Well, the first thing I notice is that I have a rational function with the denominator having a factor of x minus 3. So my guess is that there will be a factor of x minus 3 on top. So it might be a good idea to just factor the top. Well, some of you might be going, well, I don't know how to factor a cube. I remember that kind of back from Algebra 2 or Math 3. I don't really remember it, though. I wasn't very good at that. Whatever it was, the idea is if I want to fix the problem, we know we have a problem at x minus 3. So chances are there is a factor on the top of x minus 3. So let's go ahead and do some long division to see what's left over when I take out a x minus 3 or factor out of x minus 3. That'd be x squared. X squared, then multiply, then subtract. So we'd end up with negative x squared minus 17x. So that'd be negative x. So negative x squared plus 3x. We'll subtract that. So that's going to be negative 20x plus 60. That becomes negative 20. And then multiply those, that's negative 20x plus 60. And then we subtract that, and we have a remainder of 0, which means x minus 3 is a nice, clean factor. So we can actually factor this some more. We could say this is x minus 3, and then times the factors of this would be x minus 5 and x plus 4 all over x minus 3. And so we can see that we have a removable discontinuity because those factors reduce, and we're left with these two factors, which would imply that we have a parabola. So we have a parabola here, and I'm going to go ahead and multiply that out. It ends up being that, of x squared minus x minus 20. Now that doesn't mean that g of x is actually equal to this. It is equal to it everywhere except x minus 3. We know that basically g of x is a parabola with a x-intercept of 5 and x-intercept of negative 4, and it opens up. Okay? But we know that when x equals 3, we have a hole there. So that's what this graph, g of x, looks like. We have a hole. How do we fill the hole? How do we fix it? Well, we just put a dot there and fill it in. What makes it a continuous function? Well, if we were to say y equals x squared minus x minus 20 is our function, then we would have a nice continuous parabola that matches this parabola but fills in the hole. And so that's our expanded equation is what we would say. Okay? So we can say that removable discontinuity x equals 3, and therefore what's left over is how we fill the hole. All right, that ends the lesson for the idea of continuity. If you have any questions, please reach out to me. My goal is to help you as much as I can. I do not want to use any excuse for you to be struggling. I don't want to have any excuse on the table. So if it takes extra effort, if it takes extra time, if it takes me doing more on my end to make sure that you understand it, as long as you're working hard, I will continue to work hard as well. So comment below if you have any questions, or email me. Whatever it takes, I'll help you out. And until next time, have a great evening.